विज्ञान की अनकही कहानियाँ, आइए हम सुने विज्ञान की अनसुनी कहानियाँ. Hello listeners, you're listening to Vigyan Ki Awaaz podcast program on STEM popularization, catalyzed and supported by the Ministry of Science and Technology, Government of India and Media for Community Foundation. Project devised and designed by Dr. R. Sridhar and assisted by Ashish Tiwari. Local coordination and production, Professor Subramanian. Content writing by Priyanshu and post-production by Professor Kaushik P. Kanchan of Garden City University, Bengaluru. Garden City University, conquer we shall all adversity. Together we stand in unity. Together we strive for prosperity. GCU, emphasis on life. GCU, emphasis on life. Hello listeners, you're listening to Vigyan Ki Awaaz podcast program on STEM popularization, catalyzed and supported by the Department of Science and Technology, Government of India through its National Council for Science and Technology Communication and Media for Community Foundation. Project devised and designed by Dr. R. Sridhar and assisted by Ashish Tiwari. Local coordination and production, Professor Subramanian. Content writing, Priyanshu Sarkar. Post-production, Professor Kaushik P. Kanchan and Krishna Kapil of Garden City University, Bengaluru. On this episode of Vigyan Ki Awaaz, we have an esteemed guest, a luminary in the field of statistical and condensed matter physics, a prolific researcher, and a thought leader in phase transitions and critical phenomena. It is an absolute honor to welcome Professor Subir K. Das to our show. Professor Subir K. Das is a distinguished scientist specializing in statistical mechanics and condensed matter physics. His research delves into static and dynamic critical phenomena, nucleation and wetting, kinetics of phase transitions, and pattern formations in granular, active, and biological matters. His work integrates scaling theories, renormalization group methods, Monte Carlo and molecular dynamic simulations, and field theoretic models to explore science and physics.
My name is Subir Das. I work in the Theoretical Sciences unit of Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. And my domain of research is statistical physics. Basically, by using statistical physics, I study phenomena in condensed matter systems. And in condensed matter is a very broad area within the major domain of physics. And phase transition and universality related to phase transition is a more specific domain, which itself can be very big though. Now let me tell you a bit about what phase transition is. Let me start with the example of what we all notice and basically do at home: boil water. When we heat up a kettle of water, vapor comes out, so that's phase transition. High density liquid phase to low density vapor phase. Now, such kind of phase transitions with somewhat similar nature can happen in other systems also. For example, in magnetic systems like para to ferromagnetic transition, that is separated by temperature referred to as the Curie temperature or a critical point. And this critical point is common to many such phase transitions. Now, these systems are generally referred to as passive matter systems. In recent times, there have been a lot of interest in another type of systems. These are referred to as active matter systems. Active matter systems are such that where the constituents of the systems, they continuously draw energy from the environment to self-propel. What kind of, how do they draw energy? In terms of, like, we human beings are active species, active particles, and we can execute or exhibit directed motion by drawing energy in the form of oxygen or food from the environment. And we also can exhibit phase transitions. Let me tell you about some sort of cluster formation or phase transition in a collection of bars, flocking transition in a collection of bars. We often see that the bars are moving together. In some region, there are fewer number of bars, it's like vapor phase, and in some region of space in the sky, the bars are more in number. So that's clustered or high density liquid-like phase. And in all these phase transitions, over many decades or centuries, a fundamental interest has been to understand universal features. Despite lot of differences in the constituents of the systems, if there exists some sort of universality in the properties related to thermodynamics and dynamics. So understanding, first of all, identifying and understanding such kind of universality is one of my major research areas in the domain of, by applying statistical mechanical principles and methodologies.
Professor then explained to us how the Mpemba effect can be applied to active matter systems.
Recently, I have been interested in a particular type of work that is referred to as the Mpemba effect. And the story behind this effect is very interesting. Let me first tell you what or how the effect can be defined. Like in a single sentence, a hotter sample of liquid water should freeze faster than a colder sample of water when both of them are simultaneously placed inside the refrigerator. So this is very counterintuitive in a thermodynamic sense. That is because a hotter sample is further away from the final state point, which is an ice phase, than a colder sample of liquid water. Now, this phenomenon was discussed even by Aristotle more than 2000 years back, and most recently it was rediscovered by a gentleman or a schoolboy at that time from Tanzania. His name was Erasto Mpemba. He passed away in 2023, I suppose, at the age of 70. He accidentally discovered it during a cookery class in his school. Now, as I told you, the phenomena is very counterintuitive. Because of that, many people didn't want to believe it. Once he noticed this thing, he told his friends and teachers in the school. He was ridiculed by them. They said that this cannot be correct. And after some time or some months, one university professor, his name is Dennis Osborne, a British gentleman working in Tanzania, he came to give a lecture in Mpemba school. And during his visit, Mpemba asked him the same question. So he asked, because he was puzzled by this observation, he asked him why hotter water should freeze faster than a colder sample of water. And the gentleman, Dennis Osborne, was also unaware of this fact, even though it was written even by Aristotle more than 2000 years back. Then he said, oh, well, after going back to my university, I will repeat your experiment. He asked his assistant, Dennis Osborne, to do the same experiment that Mpemba told him about. And his assistant came back to him and said that, well, I'm getting the wrong result. That means the hotter sample is freezing faster, but I will keep repeating the experiment until I get the correct result. So that was quite interesting. And I have been interested recently in such kind of studies. If you look at this phenomenon carefully, essentially what it says that a system which is farthest from the final destination is arriving the earliest. It's like, say, there is some event in Bangalore, I'm coming from Kolkata, somebody is coming from, Trivandrum in Kerala, and another person is coming from Mysore. And I am the furthest to start from, and I am arriving at the earliest. So this is certainly counterintuitive, but depending upon what kind of mode of transport I choose or we three choose, it is possible that the person who is starting from a furthest distance can arrive at the final destination earliest. Now, if we generalize this phenomenon in this simpler language, then we can ask similar question for phase transitions in various other varieties of systems. So, in our group, we have investigated the presence or absence of similar phenomenon in magnetic systems, like when a system undergoes transitions from paramagnetic to ferromagnetic phase. You start with a paramagnet above the Q temperature, which is at a very high temperature, and another person starts with same paramagnetic phase region, but with a lower temperature. Then both the systems are simultaneously coins to the ferromagnetic region. The question is which one will get ordered in the ferromagnetic phase faster. It appears that one that started from the higher temperature. And we have, so even for the water case, there hasn't been any computer simulation, and theoretical works try to make some speculative guess what could be the reason. And we, in our group, for the first time showed that indeed it is possible by appropriate model construction or by using appropriate model, we showed that it is indeed possible for hotter sample of water to freeze faster than the colder sample of water. And very recently, we have been working with active matter systems that I described already, say a flock of birds or a school of fish. They exhibit a lot of phase transition, passive matter phase transition like behavior. Okay? And there you ask the question, so these phase transitions are related to, you have some sort of interaction in the system amongst the constituents, and then you introduce some noise. So there is a competition between this, say, alignment type of interaction. One particle is moving in a particular direction and others trying to follow that way. Some sort of order may emerge in the system. And then on top of that, you introduce some noise. It's like temperature in standard passive matter systems. Then there will be a competition between this noise. Noise will try to make the system disordered, and this alignment interaction will try to make things ordered. So because of this competition, like in a transition from para to ferromagnetic regions of the phase diagram, there can be phase transitions from disordered to ordered region. And then you ask the question, if I prepare my active matter samples at various different levels of noise strength, and then simultaneously each of them I coins to a final state point where it is expected that there will be ordering or cluster formation in the system. Then which one will order or form clusters quicker? And we find that actually the ones which are starting from furthest distance, that is with higher noise strength, they are getting ordered quicker. So the phenomena is rather general and universal, and my current research focuses on this.
You were listening to Vigyan Ki Awaaz, a podcast on STEM popularization, catalyzed and supported by National Council for Science and Technology Communication, Government of India. Tune in for more such episodes to Vigyan Ki Awaaz on this platform and also through Spotify, YouTube and Apple Music platforms.
आइए हम सुने विज्ञान